question 11. A rock is thrown upwards on Mars with a velocity of 19 meters per second. And after t seconds, its height is given by this formula. So a really ugly formula for the height. And they go and they ask you for things that you might not realize what they are. The first thing they ask you is what's the velocity in meters per second when t is 1 second. So you might think, how can you get velocity when all you're telling me is the height? Well, you've got to realize that velocity is actually just called a rate of change. Velocity is the rate of change of, in this case, height, time. And we haven't dwelled on it much, but rate of change is actually a derivative. And in this case, at the 1 second mark. So the velocity is really them just telling you to find the derivative at 1. So once you realize that's what it is, it makes a little bit more sense. Now, do you want me to do the h tends to 0 or the x tends to a? Since this is a quadratic, which of those two you think is going to be less work? What was my advice when you were doing quadratics and polynomials in general? Which formula, the h tends to 0 or the x tends to a one? Which one should you use?
Sure, for boiling.
H tends to 0.
Yes. So I'm going to do the limit as h tends to 0 of f of, well, technically a plus h, which is 1 plus h, take away h of 1 all over h. That's just like saying f of a plus h, take away f of a. And that becomes the limit as h tends to 0 of 19 1 plus h's, take away 1.86 1 plus h squared, take away the value of the function when h is 1, and that in itself isn't even very nice, because 19 times 1 take away 1.86 times 1 squared is a horrible decimal. It is 17.14, and the whole thing is over h. Would you agree that is one ugly looking equation? I mean, if the numbers were 2 and 3, it'd be a dead easy equation. Isn't it just 1.86s and 19s and 17.14s that are making it hard? But as long as you say, hey, it's the same as all the other ones, it's just weird and ugly, you'll get to a better place. So the velocity, which is what this rate of change is giving us, excuse me, is the limit as h tends to 0 of, distribute that, 19 plus 9h. If you take this guy and you FOIL it and then you multiply it by this, you'll get negative 1.86. Then 2h times that gets you negative, I can't do that in my head, or at least I don't want to. 1.86 times 2 is negative 3.72h, and that times h squared gets you negative 1.86 h squared, and just enough room for the negative 17.14. Scarily ugly, but really mathematically just the same as every other situation. Okay, if you take this number and this number and this number, what happens when you combine them all?
Just make 0, right?
Yeah, and shouldn't they always make 0? Isn't that the little trick that you know you're doing it right? Now, I have got a negative 1.86h squared, yikes. And I've got this guy and this guy, which gives me a positive 15.28h. Yeah, so that's what this top line becomes. Now, although the numbers are clearly really ugly, it doesn't mean I change my process. What do I do to the top expression?
Factor out H.
And so I have negative 1.86h plus 15.28. Would you agree the ugly numbers are just ugly numbers? The process is the same as it always was. Now, at this point, the same thing's going to happen that typically happens when the numbers are nice. What do we do now?
Cancel the H's and then plug in 0.
And you're done. So cancel the H's, leaves me with this. And if you plug in 0, you are left with 15.28. And they told me in the question, the answer was meters per second squared. So after 1 second, this rock on Mars is traveling at 15.28 meters per second. If I can imagine what this might look like, this is time and this is height. Won't you throw the rock in the air and then it'll come back down? And we've just found out that at 1 second mark, the velocity is that number. That's the connection between the slope of a tangent line and the velocity. The slope of a tangent line to a curve at a point can be also thought of as the rate of change at that point, which in turn, in this situation, is a velocity. So do you see that if you know where the height of something is at any time, don't you now know its velocity at any time? Does that make sense? See this point at the top of the hill? Won't my tangent line be a horizontal line? You agree? What's the slope? What number is the slope of a horizontal line?
0.
0. Have you ever done a physics class where they say that if you throw something up in the air, isn't there an instant of time where it's technically stationary before it comes back down? Can you see that's exactly at the top of the hill? Does it make sense that's where it would be? Now, when you do physics, hopefully you will, or mechanics, wherever this comes from, if the number is positive, isn't that telling me that the rock is on the way up? What happens if I do a question and the velocity is a negative number? Well, isn't that telling me it's on its way down? So don't you not only know which direction the rock is going, but you also know its velocity, right? Positive and negative numbers make sense in this question. Are we good? Now, I'm going to cheat here a little bit early, but I think you deserve it. Question B was going to be find the velocity at t equals a. So it was going to be that guy. So you were going to have to find the limit as h tends to 0 of h of a plus h, take away h of a all over h. Would you agree it would be even uglier than the one we've just got, but you would be able to do it? Because this has an a in it, won't the answer be some formula with a's in it? Agreed? You know, it'd be like 5a plus 1 or a squared minus 2a, right? It'd be a formula like that. I'm going to show you the shortcut because I think you deserve it. So forget about that question for a little while and I'll come back to it. Let's have a function called x squared. That's the original function. And here we're going to do its derivative. Right? We're going to find out what f dashed x is, right? Or actually f dashed a, because it's going to be its derivative at A. The answer is 2A. I'm not going to tell you why. Just right now, I'm just going to give you some examples and see if we can find the shortcut. Right, here are 4 functions, and over here is what, if you did it the long way, right, this way here, this is what you would eventually end up with, right? So there is clearly something going on here that allows you to jump to here without having to do all that, right? That's the shortcut. Does anybody try and explain, let's not worry about the last one, but explain what's going on in these questions? The first 3. Let's hide that one for a minute. What is the pattern? Can anybody see it?
You subtract the exponent by 1 and multiply the number by.
Yeah, and you're correct, and nothing wrong with the way you say it. I'm just going to say it a slightly different way. You multiply by the power, and then you reduce the power by 1. So you multiply by the power, right? 4 times 5 gets you 20, and then you reduce the power by 1, so you've now got A cubed. So again, I'll hide that one for a little while. If you want to find the derivative at A, multiply by the power, that gets you 30. Reduce the power by 1, you get a square, so we'll call it A squared. Minus, multiply by the power, you get 8. Reduce the power by 1, don't you get X then, and X becomes the A. Do you see how that rule works? Now, how about the shortcut is multiply by the power and reduce the power by 1. Okay, what will the 4x squared get me?
8x.
And that is then turned into AA. Agreed? What will the number -2 get you?
0.
Agreed. Now, if you think, well, how does that become 0? Everything else turned into something, but why did that -2 just disappear to 0? Well, here's a kind of pseudo proof of it. Couldn't you call -2 -2x to the power of 0? Because isn't x to the power of 0 just 1? Great. X to the 0 is 1. Now, if I use my rule then, don't you multiply by the power and then reduce the power by 1? Well, isn't 0 times anybody 0, so it just disappears. Now, let's look at this ugly one. Multiply by the power, 4, reduce the power by 1, A cubed. Multiply by the power, 4, reduce the power by 1, A. What happened to the number? All numbers disappear, right? So +5 gets you nothing when you differentiate it. -1,000,000 gets you nothing as well. Now, the guy that we are going to use the shortcut for, as ugly as it is, we can still find its derivative at A. Okay. What would 19x, 19b, 19t, what will you get when you find this guy's derivative? What does 19t get you?
19.
Okay. take away 1.86x squared or 1.86t squared. It doesn't matter what the variable name is, it's the same rule. What do? Well, you multiply by the power and then you reduce it by 1. Well, if you multiply this guy by 2, again, I'm taking no chances. Oops, try that again. You get 3.72. And don't you reduce the power by 1 to get a t, and the t gets you a. Do you see that we now have the answer to that guy without having to do all of this? Isn't that shortcut a really cool thing?
So does the x or the t or like the x, it just turns into an a?
Yeah. So if it was like a t cubed, you'll call it a cubed. Later on, we're going to call it t. Right, but right now they're still going to call it a, but later on it's just going to be h dashed of t. So if I put the variable t in here, the answer now becomes that guy. Does that kind of make sense? Not that I would ever want to, but couldn't I put the letter p in which case this answer would now become that fella, right? So it's kind of cosmetic, isn't it? That the variable name is just a letter that's used as a placeholder. Well, now that you know this is the correct formula, right? And I've lost my number. Oh, here it is. Remember that 15.28 that we got? And we had to do it this way. If I had this, wouldn't I just say, oh, the velocity at the 1 second mark is just 19 times 1. Let's try that again. It's 19, take away 3.72 times 1, which is 19, take away 3.72, which is 5.28. Wasn't that a lot quicker than having to do it this way? Do you like the shortcut? Multiply by the power and reduce the power by 1. You like the shortcut. It's going to make your life so much easier. Now, continuing with this story, but we'll use the shortcut to help us a little bit. Question C says, when will this rock hit the ground? So you remember my little picture looked something like this. It went up and it went down and it hits the ground there. And the original function is 19t take away 1.86 t squared. So they want to know nothing to do with derivatives right now, but we do want to know when this thing is 0. So anybody want to give me a method for solving this equation? So this is nothing to do with derivatives, this is to do with algebra. How could I solve this equation?
Factor to get the x-intercept.
Yeah, I agree. And I believe that's what the other person was saying as well. You agree? Now, in this case, there are two solutions. T equals 0 makes sense, isn't that the height when it started? But the one where it hits the ground, isn't it this one? So what we're looking for is, when does this factor equal 0? Well, if you subtract 19 from both sides, and then you divide both sides by negative 1.86, you will get negative 19 divided by negative 1.86. You will get approximately, we'll do the one decimal place. So you will get approximately 10.2 seconds. So that's about 10.2 seconds. So that's a long time in the air, isn't it? You'd have to be a pretty good baseball player or football player to throw a ball that lasted 10 and a bit seconds. You agree? It's a long time. But the reason this is true in Mars is, isn't the gravity in Mars a lot less. I don't know, yeah, it's a lot less. So when you throw things in the air, gravity takes a lot longer to pull it down to the ground. Have you ever seen the moon landing ones where they played golf and the guy hit the golf ball and it like went forever? No, did a little video of that. Yeah, that's what's happening. So as long as that, or as big as that seems, it's actually not that bad. So the last question they said is, find the velocity when it hits the ground. And I've already said to you, isn't the velocity just the derivative at any given point? So the velocity in this case is going to be the derivative at 10.2 seconds. And we have a nice formula for that guy, don't we? I don't know where I put it, but it's around there somewhere. I can write it down again. It's going to be 19 take away, oh, darn it, I should keep numbers handy. Two of these guys. So let's take away 1.86 times 2. Right. So let's take away 3.72 times t. So it's going to be 19 take away 3.72 multiplied by 10.2. So there's 19. Take away 3.72 times 10.2. And something really interesting should happen. That number is pretty close, if you round it off, to 19 meters per second. In fact, isn't it negative 19 meters per second? Do you remember that this story, the rock was thrown up with a speed of 19 meters per second, and it came back down, and it hits the ground at negative 19 meters per second? Isn't that, if there's no air friction and all the other things, isn't that things hit the ground at the same speed they went up? Isn't that why people get killed by bullets that are fired in the air because they're excited? So do you see those things where you see people, you know, in war-torn countries after they've had a victory and so on, they've all got these Kalashnikovs and shooting them into the air like they're happy. Do you know every single one of those bullets comes back down to the ground and kills someone if they're not very careful? And if they do it vertically upwards, won't they actually kill themselves? I always wondered what happened to those bullets. Evidently, people must be getting killed by them. So I'm wondering why you don't hear about it so much. Is it because they're on an angle and it's most of the bullets just hit roofs somewhere and nobody's up on the roof? And so a lot of them that might have killed someone just don't get it. Right. Anybody ex-military? Right. Were you told in never, ever, ever shoot your gun in the air?
That's right.
And the sergeant, if they caught you doing it, you'd be in real serious trouble, whether the bullet hit anybody, whatever.
Well, I didn't have to worry about that. I was on a sub.
Okay. You should never fire your gun in any direction on a sub.
That's right.
Okay. If it's not a secret, on submarines, I'm assuming that there are some people with guns. The security officer.
Yeah, yeah.
Right. But very rare, right?
Mhm.
Submarines are not usually used as landing vessels to attack islands, right? That's not their job. So you don't need guns for the most part. Okay. Are we comfortable about that horrible question now that I've shown you the shortcut? If I hadn't shown you the shortcut, wouldn't you have a lot of questions that looked like this to do? And that wouldn't have been anywhere near as much fun. So let's focus on the shortcuts for a little while, and then we'll return to some questions. So I'm going to muck about with the variables so we're not just doing x's all the time, although the first one I am. So if f of x was 7x cubed, take away 2x squared plus 5x minus 1, won't its derivative, f dashed of a, be multiplied by the power reduce it by 1. Multiply by the power, reduce it by 1. 5x gets you 5 and that gets you nothing. And I've just realized that since I put an A there, I should be consistent with the answer. So there's your first one, right? It's called the power rule. So let me show you as a general rule. If f of x is a times x to the power of n, and you want to find the derivative at a, oh darn it, that's a bad choice of lettering, isn't it? Oh, can't do nothing about it right now. Yeah, yes I can. Let me redo my lettering system. F of x is b times x to the n. Then won't the derivative at a be multiplied by the power and reduce the power by 1, and then replace the a with n minus 1. We call this rule the power rule. So if you want to find the derivative of x cubed or x squared, multiply by the power and reduce it by 1. Okay, let's put in some new letters. G of t is t to the 100, take away t squared plus 5t. And I want to know g dashed of a. Well, multiply by the power and reduce the power by 1 and then replace it by a. Are you happy about 100 a to the 99th power? Now what about take away t squared? Well, won't that be 2 times t, which becomes 2a, and won't the 5t become 5? So there is our answer for that guy.
For 5t, since there's no power, you don't multiply by 0.
No, 5t gets you 5, and it's just a fixed 5. There isn't any a attached to it. It's just 5. And anything that's only got a single power, like 10x gets you 10, 5p gets you 5, 20t gets you 20, right? You just get a number. Now, what about negative p to the 4 plus p squared? Somebody tell me what the derivative of that expression is, just using the shortcut method. I'll take any volunteer, just call it out.
Negative 4p cubed plus 2p.
And then we'll just replace everybody by a's for a little while longer. We're going to lose those a's really shortly. Are we cool with that? Now, the a's are really being used because of our formulas. Mathematically, if I went and said to you, a function f of x is x cubed, take away 2x, and I said to you, what's the derivative of x? Wouldn't that seem a more natural way to write your answer? Agreed? And that's actually the way we do write the answers. So those g dashed of a's and h dashed of a's that I've had to kind of work with here, you see they're going to kind of go away. And if you know this, can't you find f dashed of 1 and f dashed of 41? Second point, this guy up here, would you want to use any of the two long methods to do that guy? Can you imagine horrendous amount of work you'd need to do with 100 power? Wouldn't it fill up an entire piece of paper? Just try to write it down after you've foiled it out, right? So you know it ain't practical. Right, I want to do some more of these guys, and then I'm going to extend it. I'm going to show you some situations we haven't seen yet. So this one is just to, you know, keep with the flow for a few while. Just checking in some stuff. And now I'm going to call it g dashed of x. Okay, what you got here? What will 3x squared get me? Anybody, just call it out. 3x squared. What will that get me?
6a.
Yeah, and now we're back to x's, right? So 6x. Keep playing with your head here. What would this one get you?
2a cubed minus 2a cubed.
Right, and I'm going to call it 2x cubed now. What will the 3? What will that get you?
0.
0. Well, since this shortcut is so useful, wouldn't we want to try and use it in as many different situations as we possibly could, so that we avoid the limit as h tends to 0 or the limit as x tends to a? And in fact, a lot of what we're going to be doing over the next few weeks is finding out how to find what are called the derivatives. That's what we call these now. So this thing here is called the derivative. Sometimes they add the word function, sometimes they don't. So it's a derivative function of g of x. So that's what this is called. We normally just read this piece out and we call this, at least I call it, d dash x. I think Americans call it g prime x, don't you? Is that right? I don't like prime. I'm not going to change it. I'm calling it g dash x. You call it g prime x and you're totally good. Side story. Other professors who teach calculus know which ones I've taught. So if you do Calc 3 with someone else and they ask you for a derivative and you will say g dashed of x equals something, they will say, you got Professor Robertson, didn't you? And it's not me. I'm not the one person in the world that does that. If you go to Scotland and England, they call it that there as well, right? So it's not just me. It's just an idiosyncrasy that Americans think it's called prime. Oh, here's another one while I'm at it. Have you noticed that I call that brackets? I say 7x plus 3 in brackets. You know, I use that term.
The parentheses.
Parentheses. I'm too old to change my mind. After I've said it a few times, don't you know what I'm talking about? So, you know, if I say 7x plus 3 in brackets, you know what I'm talking about. I hope. So here's the new guy in town. I would like to differentiate that guy. I'd like to find his derivative. And I want to use the power rule. But the way it's written isn't helping me. I can't see how to do it the way it's written. So what you're going to do is you're going to write it as a fractional power. Can you remember square roots are half powers? So far, so good. Now, isn't the shortcut multiply by the power and then reduce the power by 1? So let's see what happens when I do that. And I wouldn't normally write this line, but I am going to do this one. Multiply by the power and then reduce the power by 1. Well, those two guys get me 2. And if you take 1 away from a half, you get negative a half. Are you comfortable with how I found the derivative? Still using the power rule. Now we're going to do a thing that I call style points. Style points is we want you to write the answer in a way that everybody agrees is the best way to write an answer. And the rules for style points are, the first major rule is make the answer look like the original f of x. Now, didn't the original f of x have square roots in it? So style points, the way people in the mathematical world have decided certain rules is that the answer should look like this, right? It should have square roots in it. And the second, there are 3 rules, so I'm glad there are only 3. The second rule is factor the heck out. If the thing you've got can be factored, right? Factor it, right? Factor the heck out, right? And the third one we won't meet until a lot later. Use trig identities. Now that third one will only play in functions that have got, sine x's in them, right, and cosine x's and sine squares. So you won't worry about that third one for a few weeks. Right, now, mathematically, that guy doesn't look like him. First thing I'm going to do is use a property that says negative powers can be written as fractions. So x to the negative a half can be written like that. Are you comfortable with that? Negative powers can go downstairs. Right? And now that I've written it that way, can you see that I can now turn it into the guy I want? And so this would be regarded as the proper version of the right answer. Now, there are a couple of advantages to that. The first one is, isn't it dead easy for you to check your work with someone else? Because don't you both have the same answer? Second one, if I'm going to do calculations, would you agree when x is 4 or 22 or 7, isn't that much more obvious what the answer is than if you wrote it like that? Now, if I said x was 100, you'd be saying 2 times 100 to the power of negative a half. You'd be kind of hard pressed to know exactly what you have got there. Agreed? In this case, isn't it 2 over the square root of 100? And that's pretty obvious what you've got, because most of the time we want exact answers, not decimals.
Do we not rationalize the denominator?
The good news is, no, you don't need to. In the number world, yes, you should. But in the algebra world, that is considered okay. Why we don't, not that you couldn't, and if you did, you'd be totally correct, and I would never take a point off for someone doing that. But if I did rationalize the denominator, can you trust me that would be the answer? And then you should say to yourself, which of those two answers looks the nicest? So can you see why most people stop there? And that's the only reason. Is that correct? Yes, but we tend to have our own little baby rules. Like, that's nicer, we'll keep it. Let's try another one. Let's call it G. Let's call it G of t. And G of t is going to be 4 cube root of t. First things first, what fractional power will I rewrite this as?
1/3.
1/3. Now the power rule is going to come into operation. I'm going to multiply by a third, and I'm going to take away 1. Are you happy with that? I'm then going to move it downstairs, so it looks like that. Are we comfortable about negative powers becoming positive powers on the bottom, which is an algebra thing? And then you might not be quite as comfortable with this guy. That guy has to look like him. T to the 2/3 is actually the cube root of t squared. Can you remember that from when you did radicals? So this guy is a cube root of t squared, and now we are finished. So doesn't that mean that we can now do square roots and cube roots and 10th roots of things? We now have a shortcut that allows us to find those guys. Right, let's move it on to still on radicals, cube roots, and square roots. And I'm going to differentiate 10 times the cube root of x squared. It's pretty much the same kind of situation. I'm going to have to write it as a fractional power. Great. What fractional power is the cube root of x squared? Because there's 2 ways to write it, but only one's right.
2/3.
Agreed? Right, the radical goes in the bottom, the power goes in the top, so 2/3. Now, when you differentiate with the power rule, you multiply by the power, which gets you 20/3. You reduce the power by 1, you get that. I will then bring this guy downstairs, which we've done quite a few times, and make it look like the original. And x to the 1/3 is just simply the cube root of x. This is kind of connected to Vanessa's earlier question about rationalizing the denominator. Would you agree trying to rationalize that is not even a starter? Right. Cube roots don't rationalize well, right? So that's another reason for leaving it alone. So far, so good. Right, so if I give you any kind of cube root, square root, fourth root guy, do you feel comfortable about its power rule? Can we move on? Everybody good? Right. Well, that's how you take care of radicals. Suppose somebody gives me, and you can only really do simple fractions, but suppose somebody gives me a simple fraction like 10/x². So I'm going to show you how you do 10/x², 5/x², 7/x, right? There isn't anything really ugly in the bottom. It's always going to be an x³, an x², that kind of thing, right? And there's going to be a number on the top most of the time. If I want to differentiate this guy, I have to find a way of writing it so that it's a power of x. That way I can use the power rule. What power of x is 10/x³?
-3.
Yeah. Aren't we using the rule negatives go in the bottom in reverse now? You see, we're using that piece of algebra in a different context, a different way. Now, I can find the derivative of this guy by multiplying by the power and then reducing the power by 1, which wasn't too bad, right? Style points. Make it look like the original. Make that guy look like the original. Any suggestions?
Is it -120a to the over a to the
No, you don't need to do any more multiplication.
Okay,
But what would I do with that to make it look prettier?
Is x
You
to the
bump x
fourth
forward
on the
then.
bottom?
Yeah, I wasn't clear with my question. Right, that's what I wanted. You agree? Looks nice. Right, now, the last few moments, let's look at this fella. I want to find the derivative of this guy, right? And they're going to call it, what do they call it? Oh, they're going to call it the velocity again, right? And I want to find the velocity at t=a and t=1, and who cares, t=2 and so on. First thing I'm going to do is use the shortcut. So won't this guy be called 8t to the -2? Agreed? And then I'm going to do the derivative, multiply by the power, right? And reduce the power by 1. Be careful here. What do you get when you reduce -2 by 1? What power do you get?
-3.
-3. Then make it look pretty. Style points. And since they want, well, question A wants that guy, won't we then bring in the A's for a little while longer? And that is the answer. Now, if they want S'(1), don't you just go -16/1³, and there's your answer. And if you want S'(2) or 22, can't you just use this formula, right? With 2 cubed in the bottom or 10 cubed in the bottom. And what do they ask for? 1, 2, and 3 as well. And that is perfect timing because we have finished that section. And when we come back tomorrow, we're going to start looking at using the shortcut method to find even more derivatives.